All right. G for gas. These are G's. It is an L. That's an L for a liquid. And again, we use the script L because it's hard to tell if you just write a lowercase l, whether it's an I or a 1 or an L. Okay? All right, let's take a look at how this equation differs from these others. Up here, we have two ionic compounds. Ionic, ionic on the left-hand side, and we end up with two ionic compounds. Okay? Right here, we have something that's by itself and an ionic compound. Okay? So there's ionic compounds here. Okay? In order to have single or double replacement, you almost always have to have at least one ionic compound. Okay, it doesn't always happen that way. It's an absolute, but it's a really good guess. In this case, there are no ionic compounds. Both carbon and hydrogen are both covalently bonded. They're both nonmetals. So this is not going to be single or double replacement. Further, this is a hydrocarbon, and I'm reacting it with oxygen. So this has to be, for this class anyway, has to be classified as a combustion reaction. Okay? This is a combustion reaction. So we started out with a single replacement reaction. A double replacement reaction. Then we did a single replacement reaction. And now we're doing a combustion reaction. And you recognize a combustion reaction because you're using a hydrocarbon fuel and oxygen. Okay? Now, I've purposely put one on here that's a little complex. Okay? Because there's some things I want to show you about balancing equations that will help you. Okay? All right, so let's go through and do our atom inventory. Here's, yes. No, that's not the only thing. You have a hydrocarbon fuel and an oxygen. Okay? Notice that every time we have a hydrocarbon fuel and oxygen, we're always producing the same products. We're always producing carbon dioxide and water. Every time. Later in this unit, you've got to be able to predict that when it happens. Okay, we're not quite there yet. We will be getting there in this unit. Okay? All right. How many carbons on the left side? Good, 4. How many hydrogens? How many oxygens? Okay. Whenever I have carbon dioxide and water as a product, it always comes out to be 1, 2, 3. You can count them, and you should, but I've been doing this a long time. It's always 1, 2, 3. I'll list them as carbon, hydrogen, oxygen. Okay. Write it like a sneeze. You get 1, 2, 3. All right. So, what are we going to say for last? What's next to last? Oxygen last, hydrogen next to last, so that means we must start with the carbon. I have 4 carbons on this side and only 1 on this side. I must put a coefficient of 4 out in front here. Okay? Making this a 4. And now I've got 4 times 2 oxygens. So the number of oxygens I've got are 8 here plus 1. I currently have 9 oxygens. Okay? Now, don't do this in your head if you're not really good at keeping up with these numbers. I'm putting my addition out here to the side just to make sure I keep up with it. When's a shortcut not a shortcut? When you get lost. So don't get lost. Use your tools. You got a writing tool here. Use it. Okay, what's your question? I added up the oxygens. I have 4 times 2 oxygens because the 4 coefficient multiplies everything in there. This 2 next to the oxygen means I started out with 2 oxygens. Now it's 4 times everything. So that's 4 times 2 is 8 oxygens here. There's the 8. And 1 oxygen here. That's 1. So you add them together, you get 9 oxygens. That's what I put down here. Okay? All right. Now let's see. We got the oxygens that evened out, but we had to redo the oxygens here. I mean, we got the carbons fixed, and we had to redo the oxygens. Since we're going to say for our oxygen is last, we need to balance the hydrogens next. So how do I get 10 hydrogens on the right-hand side? Put a coefficient of 5, and that's 5 times 2, so that's 10 hydrogens. But guess what? We changed the number of oxygens. All right, so we know 4 times 2 is 8, plus 5 times 1 is 5, so we have how many oxygens?
We messed up the oxygens because we could have 5. Okay.
Now this is where we got, and this is why I gave you this one on purpose, because for some reason, students tend to get to a problem like this on a test or homework or classwork and just stop. I can't do this, Mr. Tatter. Okay, it's a real simple solution to get past this. Really simple. Okay, everybody hear me? How simple is it? Really simple. Okay? All you have to do when this happens is go through and multiply all the coefficients except the one in front of oxygen by 2. Multiply all the coefficients except the one in front of oxygen by 2. If you end up with a situation where you've got an even number of oxygens on one side and an odd number on the other, you get past this little roadblock by multiplying all the coefficients except the one in front of oxygen by 2. We'll get there. Yes, we'll get there. Just be patient. You're ahead of everybody, and that's okay. It's great if you can do it. What? I'm going to show you. But right now, I want to make sure everybody's got this rule down. Okay? This is the only thing that's just oxygen. Okay, if you have a situation where you've got an odd number of oxygens on one side and an even number of oxygens on the other. An odd number of oxygens on one side and an even number of oxygens on the other. You want to go through and multiply all the coefficients by 2.
Multiply all coefficients?
All the coefficients by 2 except the coefficient in front of the oxygen itself.
And there's the oxygen on both sides? You don't do?
Well, all we have is one oxygen here. The rest of it's oxygen combined with something. Hmm? Oh, I'm sorry. You moved, didn't you? Oh, that's all right. Yeah, you're not where you're supposed to be. Oh, that's not good.
Yeah. Not in food. Not in food.
Your head's down. You're sleeping. Okay? What happens if you sleep in my class? No, you lose your desk. You stand. Okay? All right. Yes?
Why, like, on the oxygen where you got the 2 dots and 8.5 equals 13,
Yeah.
why 6 plus 5?
Okay, there are 5 oxygens right here. That's the 5. 4 times 2 is 8, plus the 5 comes from right there.
I thought you used
And you have to add them together because there's a plus sign right here in the formula, in the equation. Okay? All right. Now let's go through and do that. Let's put a 2 here. Let's change this 4 right here to an 8. Let's change this 5 right here to a 10. I got to go through and change all this too? Yeah. Okay. Well, now we have a 2 times 4 carbons. That's 8 carbons. Got 2 times 10 hydrogens. That's 20. We're going to leave the oxygen alone for a moment. Got 8 times 1. That's 8 carbons. Now the oxygens are a little more complex. We got 8 times 2 is 16. 10 times 1 is 10. So we've got a total of 26 oxygens on the right side. Well, nope, there's not an easier way to do this. You got it. There you go. We're there now. Because, well, you don't, it's not hard to memorize. It's a lot of steps back and forth till it works out. Okay? Never give up. Don't give up. Okay? All right. And so now if we put that 13, as Tylen said, this changes to a 26 and everything works out.
Okay.
Now, do you see the... Oh, yeah, I didn't make that.
No, you got it right.
I didn't put the 20 over here. So there's 10 times 2 is 20, yeah. Okay. All right. All right, now imagine trying to do this without an atom inventory. That'd be pretty tough, wouldn't it? Okay? And this is a fairly simple reaction. It's not that complex. There's some lot more complex reactions than this. All right, this is about as complex as we'll probably get in here. But you can do this stuff. Okay? You can do it. All right, so those are combustion reactions.